Hello, welcome to Unit 4, Lesson 14, Absolute Value Functions, Part 2. Learning objectives for this lesson, you'll be able to describe the effects of adding a number to the expression that defines an absolute value function. You will be able to explain the meaning of the absolute value function in terms of distance. And when given an absolute value function in words or in function notation, you will be able to make sense of it and create a table of values and a graph to represent it. So in lesson 13, we introduced this idea of a new type of piecewise function, which is called an absolute value function. We looked at a cube or a jar of snap cubes, and we tried to guess how many were in there. We then graphed the actual guess and the absolute guessing error, which, if you recall, that was how far off the guess was from the true number of snap cubes. And when we plotted everyone's points, we saw that it made a nice little V shape. So today we're going to continue looking at absolute value functions, and we're going to try to really make sense of them in terms of different situations, and just have a really solid understanding of absolute value functions. We are going to skip the first activity though, so let's go on to the next one. All right, so in this activity, you are given function A, and that function gives you the distance of x from 0 on the number line. So x is our input, which is the number on the number line. A of x is our output, which is the distance that number is from 0. Okay, so go ahead, pause the video, and fill out both the table and the graph for question 1. All right, let's take a look. So here, if x is 8, I know that that is 8 spots from 0. For a of x is 5.6, there are 2 possible answers, right? And if I look at the structure of the overall table, I notice that my positive values are on top, my negative values are on bottom. So my input could be positive 5.6 or negative 5.6, but I see that negative 5.6 is already being used, so I'm going to use positive 5.6. For pi, that is just pi distance from 0. We don't want to estimate because they didn't estimate, so we can't estimate either. For 1/2, that is also half away from 0. For when the output is 1, again, we could have 2 possible inputs, -1 or +1, but we see that -1 is already being used, so we're going to use +1. When the input is 0, the output is 0. -1/2 is +1/2. -1 is 1. -5.6 is 5.6. And then 8 for the output, again, you can have an input positive or negative, but the positive 8 is already being used, so let's go ahead and do -8. All right, so I'm going to go ahead and plot the points, and then you'll be able to see all the points plotted once I'm done. So here is our graph of this function. We can see that this makes up an absolute value function. It has that same properties of it being V-shaped, symmetrical. If we were to put a mirror directly through the middle of the graph, it would mirror each other on each side. One other thing I want to point out is that notice the vertex falls in the origin. So this is the vertex of our graph. All right, let's take a look at question 2. So question 2 says Andre and Elena are trying to write a rule for this function. Andre writes a of x equals x if x is greater than or equal to 0, negative x, or another way to interpret this is the opposite of x if x is less than 0. Elena writes a of x equals the absolute value of x. So remember, these symbol bars mean absolute value. Explain why both equations correctly represent function A. So go ahead, pause the video, and answer that question. All right, so when looking at Andre's rule, Andre's works because he takes into consideration that it is a piecewise function that has two separate rules. So Andre's rule says when x is positive or 0, the distance from 0 is x, right? We don't have to worry about anything. When x is negative, though, the distance from 0 is the opposite of x. So therefore making it a positive value. So that's Andre's rule. Elena's rule is just flat out saying that the distance of x from 0 is the absolute value of x, which is always positive. So Elena's rule, let's refix that. Rule is saying the distance of x from 0 is the absolute value of x, which is always positive. So remember, absolute value functions are just another piecewise function. And what's nice about absolute value functions is that instead of writing it in terms of cases like Andre did, we could just write it using the absolute value symbol, and that helps us recognize that the graph is going to look more like a V than anything else. So there are a couple different ways that you could represent the absolute value functions. So let's go ahead and take a look at activity 3. So for activity 3, it says here are equations and graphs that represent 5 absolute value functions. Notice that number 2 appears in the equations for functions g, h, j, and k. So for example, function g is the absolute value of the difference of x and 2. Function h is the absolute value of the sum of x and 2. Function j is the absolute value of x minus 2. And k is the absolute value of x plus 2. So describe how the addition or subtraction of 2 affects each graph of each function. And then think about a possible explanation for the position of the graph. How can you show that it really belongs where it is on the coordinate plane? So go ahead, pause the video, talk about it in your table groups, and see if you can answer those questions. All right, so looking at these graphs, the first thing I want to point out is that this first graph here, which is just f of x is equal to the absolute value of x, this is called the parent graph. And we're going to reference parent graphs some more when we get to quadratics. But parent graph just tells us if nothing's being manipulated, nothing's changing, nothing's shifting, nothing's flipping, it's literally just, in this case, the right side and the left side both have a slope of -1 and +1, and the vertex is in the origin. This is considered the parent graph. No shifting has occurred. When we look at g of x, notice that it shifted, the origin or the vertex shifted to the right. And the reason for that is that our y-intercept went from being 0 over here to +2 over here. Now you may ask yourself, or maybe saying to yourself, well, it's -2, so wouldn't the y-intercept be -2? Well, let's think about what y-intercept means. It means what is the value of y when x is 0. So if I were to plug 0 into this function, I would have 0 minus 2, and then take the absolute value of that. So the absolute value of negative 2 is just 2. So we can see that the y-intercept stays at a positive 2 because we're taking the absolute value of that number. And since we're not adding or subtracting anything after the fact, we know that the y-intercept is going to be positive 2. Now you may ask yourself another question, well, h also has a y-intercept of positive 2. So how do we know which one belongs to g and which one belongs to h? To answer that question, we look a little bit closer at the x-intercept, right? So we were talking about the y-intercept, now let's look a little bit closer at the x-intercepts. So if you recall, x-intercepts are when the y value or the output is 0. So essentially what we're looking for is what value here will make it so that you end up with 0. Well, if we have x minus 2 equals 0, the only thing that can be is a positive 2. Over here, if we have x plus 2 equals 0, the only thing that can be is a negative 2. So what does that mean? It means when you have addition and subtraction happening inside the absolute value functions, you are going to end up with a shift to the left or right. So adding or subtracting inside absolute value symbols. Okay, you're going to shift to the left for adding, right? Because if you're adding, that means you need a negative x-intercept. And then shift to the right for subtraction. And again, that's because you need a positive x-intercept for when you're subtracting. So that causes a shift to the right. So let's take a look now what happens when you are adding and subtracting after you take the absolute value of x. And notice here that your shift is happening up and down. So, and that if we think about that, right, our y-intercepts and our x-intercepts are changing. We went from having a y and x-intercept of 0, but for then minus 2, our x-intercepts became positive 2 and negative 2. And for the other one, we have no x-intercepts, so there's none here. But let's talk about the y-intercept. Let's focus on that for this one. So here, our y-intercept is negative 2. Here, our y-intercept is positive 2. So again, think about what does y-intercept mean? It means when x is 0, what is y? So if I take the absolute value of 0 and then subtract 2, that means my y-intercept is going to be negative 2. If I take the absolute value of x and then add 2, that means my y-intercept is going to be positive 2. So when adding and subtracting outside of absolute value symbols, you're going to shift up for adding and then shift down for subtracting. So although yes, you can memorize this, it's very helpful to know why the shifts like that are occurring and have a better understanding of that, because sometimes we forget these kind of rules. So try to think about the x and y intercepts and what's happening to those and causing that shift. So in this activity, I want to point out that the adding and subtracting were only happening either inside the symbols or outside the symbol. But there are times when the adding and subtracting happens to both. So when that happens, you got to think about how you're going to be shifting. Let's go ahead, take a look at the last activity. So this activity is applying what we just did in the previous activity. So you're going to match each equation with the graph that represents it. There is one equation that does not have a match. For the equation without a match, sketch a graph on the blank coordinate plane. And then you can use Desmos to check your answer if you want, or you can just wait until the video is unpaused and you can check at the end. So go ahead, pause the video, and go work on that. All right, so let's take a look at graph A first. So I notice graph A shifted down to -6, meaning my y-intercept is now -6. Because it's shifting down, I know that my subtraction is happening outside of the absolute value symbols, so that would make this equation 3. For B, I shifted to the right. So my x-intercept became +3. So I know the shifting, since I shift to the right, I know I'm going to be working inside the absolute value symbols. So if I think about if my x-intercept is 3, how can I make 3 into 0? Am I going to add 3 or am I going to subtract 3? Well, I know x minus 3 would give us 0. So that tells me I'm going to work with equation 1 because that's the one with subtraction. For equation C, there's 2 shifts happening. I see I have a shift to the left, right? So everything went to the left. And then I also went down to -6. So if I thought about just the shift prior to moving down, so just if I were to focus on the shift to the left, it would look like this. And that would tell me my x-intercept is -3. So in order to, if I want y to be 0, I would have to do -3 plus 3. So that tells me inside of the absolute value, I'm going to have x plus 3. Oops. But I also have a shift down. So that means I'm also going to be subtracting 6 outside of the absolute value symbols. So that tells me this is equation 5. Next one, again, we have 2 shifts happening. First, we see there's a shift to the right for 9. So if I think about that shift to the right first, my graph would look like this. And that would give me an x-intercept of +9. So if I want y to be 0, that means I would have to do x minus 9 to get that to be 0. Then I also notice, though, that there is a shift up 3. So I'm going to have to add 3 outside of the absolute value symbols. So that would be equation 2. So I used equation 3, equation 1, equation 5, and equation 2. So that leaves us equation 4. So that is y is equal to the absolute value of x plus 3. So this only has one shift. So I'm going to shift to the left 3. And the reason why I do to the left 3 is because in order to make this equal to 0, I would need a -3 plus 3. So this tells me my x-intercept is -3. Okay. My slope is 1. Nothing has changed with my slope. So my line would look like this and like this. Alrighty, so that's it for this lesson. One thing I want you to think about is just remember that shifting can occur with these absolute value functions. So for example, this here is the absolute value of x. There are 2 different ways that we could write this function in terms of an equation. So we could say a of x is equal to just the absolute value of x. And we can also write it as a piecewise function. A of x is equal to x if x is greater than or equal to 0, and the opposite of x if x is less than 0. Notice for this graph that none of the points lie below the x-axis, and that's because when we take the absolute value of x, you can't have a positive number, or I'm sorry, you can't have a negative number. It has to be positive. If we know that a of x is equal to 4, so the output is equal to 4, we can figure out what values of x would make this a true statement. So we want to think of the numbers that are 4 away from 0. And so in this case, x can be 4 or -4 because both of those are 4 away from 0. If we know, let's say that x is equal to -5, we can use the equation to help us solve that. So a of -5 is equal to the absolute value of -5, which is equal to 5. So we can plug it into the equation to help us. We could also use the case notation to help us figure that out. So we want where input is -5, so that tells us that our cases notation we're going to focus on is the second rule, because that's where -5 is going to fall, is in this interval. So because x is -5, this tells us to take the opposite of -5. Remember, it doesn't mean it's going to be -5. In this case, the negative sign means the opposite of -5, which is 5. All right, so that's it for this lesson. Feel free to read through this summary if you need a little bit more of a breakdown, but you should now work on your cool down. Thanks for watching.